Hello students, welcome to the second session of digital circuit subject regarding smart revisions, right? So just before, in the previous session we have discussed regarding the first two chapters, that is number systems and codes and then Boolean algebra and KMFs. So in this particular session we are going to discuss regarding the remaining chapters of digital circuit subject. So this subject is common for 4 branches: EC, electrical, instrumentation, computer science. So whoever missed the earlier session, so kindly watch that session in your free time, and whoever attended that session, now you people can easily correlate what I am going to discuss in this particular session. Okay, so whoever attending very first time regarding this particular session, no issue at all. So currently you can watch this complete session, and regarding the previous session, whoever missed it earlier, so kindly watch the session also in your free time. Okay, so from these two sessions together regarding digital circuit subject, you are going to get the complete understanding what are the important points, formulas, everything regarding the digital circuit subject. You are able to get in the less time the complete revision of digital circuit subject. So all of you will get maximum benefit from these two sessions. Okay, yeah, all of you put the heading, the next chapter, that is logic gates. Chapter 3, logic gates implementation. So whatever the logic gates we are having, we can classify into 3 types. First one is basic gates. Second one is universal gates, and third one is special gates. Okay, so regarding basic gates, we are having AND gate, OR gate, and NOT gate. So these are the basic gates, because by using the combination of these gates, we can implement any Boolean function, or we can represent any digital circuit, whatever may be the, either it is a simple circuit or it may be the complex circuit, no matter. Okay, so earlier we have mentioned that we can use, whenever you are having 2 variables among which you can perform either logical AND or logical OR, wherever or whenever we have to represent a variable in the complement version, that time we will use NOT gate, that's all. Okay, and then regarding universal gates, we are having 2, NAND gate and NOR gate. And coming to the special gates, we are having XOR and XNOR. XOR and XNOR are special gates. Okay, right. So regarding complement operation, first let us see. AND gate complement is what? NAND gate. OR gate complement is NOR gate. Complement of OR is NOR. Similarly, XOR complement is XNOR. XOR complement is XNOR. Okay, for NOT gate, NOT gate other name is inverter. NOT gate other name is inverter. The complement of NOT gate is buffer. Complement of NOT gate is buffer. Okay, right. So this is about, in general, whatever the logic gate, one logic gate if you are having, for every logic gate you will be having the corresponding complement. Okay, similarly vice versa. Okay, and next one is regarding AND gate, dual is OR gate. Regarding AND gate, dual is OR gate. Similarly, OR gate dual is AND gate. Okay, similarly NAND gate dual is NOR gate. NAND gate dual is NOR gate. Okay, and can you tell what is the dual of NOT gate? Any guess? And similarly, what is the dual of buffer? Any guess? We already covered that part in the previous chapter, in the previous session. So with that understanding, can anyone mention what is the dual of NOT gate, what is the dual of buffer? It is very important. Regarding XOR and XNOR, in general those two are complement each other. Only for two input case, those two are dual to each other also. Okay, only for two input XOR gate, and two input XOR gate, these two are dual to each other also. For generalized case, those two are complement each other always. These two are complement each other. But for two input case, they are complement each other. They are dual to each other also. Okay. Coming to the NOT gate. Dual is same. NOT gate dual is same. NOT gate only. Similarly, buffer dual is same. Dual of buffer is same. See, earlier we have mentioned examples. Yeah, Jitendra. Yeah, generally sometimes students will think that NOT and buffer are dual to each other. But regarding duality, what we have mentioned, we have to interchange only the logical and logical OR operators, and if zeros and ones are there, we will interchange. But the variable, if you are having normal, we will keep as it is. If you are having complement version, we will keep as it is. Okay, we won't change the variable normal into complement or complement into normal. Okay, so that is the reason for NOT gate dual is same, for buffer also dual is same, buffer only. Okay, or we can say these two are what? Self dual. Okay, so here just for easy understanding, if you want, I will represent like this: y equal to a bar, here y equal to a. Okay, whereas if you are having AND gate, A and B you are having, dual is A plus B. That means A we have kept as it is, B we have kept as it is. We haven't modified, right? So I hope it is clear for everyone. Now coming to the regarding all the logic gates, I hope all of you know when the output will be equal to 1 or when the output will be equal to 0, etc. But regarding XOR, XNOR, okay, I will give the conclusion points. For generalized case, I will give the conclusion point, so that whenever you are having two inputs or more than two inputs, with the help of that generalized condition, you can write the output 1 or 0. Okay. So output of XOR gate is equal to 1. Just remember one case, no need to remember two. Okay, just remember for one case. Output of XOR gate is equal to 1 if odd number of ones are present at the input. If odd number of ones are present at the input. Okay, if number of ones are odd, that time you will get output of XOR gate is 1. So here regarding XOR gate, you can remember here in the XOR gate the letter O is there, in the odd also letter O is there, right? So just remember one case. For XOR gate, if you are having odd number of ones at the input side, output you are going to get 1. So that means for remaining combination you will get 0. Similarly, with this understanding, since we have told XOR gate and XNOR gate are complement each other, so XNOR gate will produce 1, exactly opposite. Here I have mentioned odd, now we have to mention even. If even number of ones are present at the input. If even number of ones are present at the input. Okay, so regarding logic gates chapter, you will get 2 or 3 variety of questions. One variety is they will give some circuit diagram, they will ask the output, or in order to get so and so output, what is the condition for inputs? That is one variety. Okay, so those questions you can easily solve with the help of the basic knowledge of these logic gates. Okay, with the help of truth tables, okay, you can easily solve most of those questions. And one more interesting question they will ask, in order to implement any particular logic function or any logic gate, what is the minimum number of NAND gates required or what is the minimum number of NOR gates required. This is one of the most important question or model in this particular chapter, and especially here while answering these kind of questions you have to read the question carefully. In some question they will specify that only normal inputs are available. If they don't specify anything about the inputs, by default you can assume that inputs are available in normal form. Okay, but in some question they will specify that the inputs are available in both normal form and complement form. Whenever the complement form also available, if they mention, that time the answer will slightly vary. So you have to carefully read the question, especially while you are answering the questions regarding minimum number of logic gates. Okay. So now I will give the complete tabular form, okay, for implementing all these logic gates like AND gate, OR gate, NOT gate, XOR gate, XNOR gate. What is the minimum number of 2 input NAND gates, minimum number of 2 input NOR gates required if only normal inputs are available, and similarly if normal and complement inputs are available. Okay, with the help of this tabular form during the gate exam you can easily answer those kind of questions. So here first column you can mention logic gate. So we are having NOT gate, then AND gate, OR gate, then XOR gate, XNOR gate. So other than NOT gate, remaining all the logic gates we are considering for 2 input case. Okay. Next, here minimum number of 2 input NAND gates. Next, similarly minimum number of 2 input NOR gates. Here if the inputs are available in only normal form. Next, here the heading is if the inputs are available in both normal and complement forms. In both normal and complement forms. Similarly, these 2 headings you can copy here. Minimum number of 2 input NAND gates, minimum number of 2 input NOR gates. Okay, right. So first of all, consider NOT gate. NOT gate means output is what? A bar. Output is A bar, right? So regarding NAND gate, so here you will write A into A whole bar, that is nothing but A bar. So it is just like AB bar. Okay, we require one 2 input NAND gate. If you are connecting both the inputs same, then you are getting NOT gate as the output, right? Similarly, regarding NOR gate, so A plus A whole bar is nothing but A bar. A plus A whole bar is nothing but A bar. That means both the inputs of NOR gate you have made same. So then that 2 input NOR gate will behave as NOT gate. Okay. So here also we require one. And coming to the NAND gates, coming to the NOR gates, when the inputs are available in both normal and complement forms. This is the most interesting thing. Inputs are available in both normal and complemented. So here output expression we are getting A bar. Y equal to A bar you are getting. So here since they have mentioned the complement inputs also available, that time we no need to generate. Okay, we no need to use any logic gate because A bar is there, you can directly consider. Just like in any logic gate, by default the inputs are available in the normal form, right? Suppose if you are considering 2 input logic circuit, A, B are available in general. Suppose if you are getting the output function as A, so whatever the input A you are having, you can connect with the help of one wire, that's all. Okay. But whenever you are getting A bar, we have to pass that A input through a NOT gate or through a NAND based inverter or through a NOR based inverter. With the help of that we are getting A bar. Okay, provided in general if the inputs are available in normal form. But in the question if they specify that inputs are available in both normal and complemented, that time we no need to generate the complement inputs. Okay, this is the most interesting thing. Whenever you are answering any question regarding this logic gates, minimum number, always they will ask the question regarding minimum number, and based on the type of inputs the answer slightly variation will be there. In few cases maybe same answer, but in most of the cases I can say the answer slightly difference will be there. So that's why you have to be very smart while you are answering these questions. Don't be overconfident while you are attempting these questions. Okay, so you solve the question based on the knowledge, based on the concept which you know, with the help of Boolean algebra or with the help of K-map or with the help of logic gate simplification, whatever the knowledge you are having, you can do it. But before attempting the question, you just read the question carefully according to what context they are asking. Okay, as per that context, you can mention your answer. That's all. Okay, that is the most important. Right. Next one is AND gate. AND gate means what? AB you require. AND gate means AB. You require AB. Okay, but here since you are using NAND gate, by default you will get complement. By default you will get complement. This NAND gate output will pass through NAND based inverter. So that means AB bar whole bar is nothing but AB. AB bar whole bar is nothing but AB. So here we require 2. Here we require 2. And similarly here also same answer 2. There is no modification because here AB are both are in normal only. For AB bar we require 1 and then whole bar 1 more 2. Okay, next. Okay, I will answer regarding NOR gates in some time. Okay, now I will explain regarding OR gate. Regarding OR gate, A plus B. Okay, regarding OR gate, first I will explain with the help of NOR. After that I will come back for NAND. Okay, so here with the help of NOR gate, first of all we are getting complement version A plus B whole bar. So for that we require one NOR gate. After that you will use one more NOR based inverter. Okay, so that means we require 2. Since here we require 2, there also 2 because both A, B are in normal form only. After that we require 2 times complement. For first one we require one NOR gate. After that one NOR based inverter. So that means we require 2. We require 2. Here 2, 2. Here 2, 2. Same. Okay. Now whatever the logic here we have done, same logic here also. But after that slides, one more step we have to do. Here we want AB. For that we will apply 2 times complement. As it is. But now we have to implement by using NOR gate. NOR gate means in general you will be having like X plus Y whole bar format. But here you are having A and B. Okay, so that is the reason we have to apply De Morgan's law here. AB bar is nothing but A bar plus B bar. Now you keep external complement as it is, external complement as it is, right? So for A bar we require one NOR gate, for B bar one NOR gate. After that, A bar you can consider like X, B bar you can consider like Y, X plus Y whole bar, third NOR gate, right? So that means we require 3 2-input NOR gates, 3 2-input NOR gates. Okay. Similarly, whatever the logic here we have done, same logic here also. A plus B 2 times complement, but here we have to implement with the help of NAND gate. So NAND gate means you are getting like XY whole bar format, but here you don't have, right? That is the reason we have to apply De Morgan's law. So you will get A bar, then B bar, and keep external complement as it is. Now for A bar you require 1, B bar 1, and this one 1. So you require 3. Now with this understanding, so regarding NOR gate there, regarding NAND gate here, can you answer how many 2-input NOR gates we require? How many 2-input NAND gates we require? Any guess? When the inputs are available in both normal and complement form. All of you just give a try. Regarding XOR gate, here answer is 4. With the help of NAND, you can remember this answer. Similarly, XNOR gate, regarding NOR gates, it is 4. And here it is 5, here it is 5. Okay, generally in the classes we used to discuss how we are getting 4 or 5, but since it is a revision class, I am not discussing in detail. Okay, you can remember easily. So for XOR gate we require 4 NAND gates, okay, and for XNOR gate 4 NOR gates. Okay, here answer will be either 4 or 5. Just remember here, okay, XOR gate 4, XNOR gate 4 NOR gates. Okay, after that for other case 5. See, here I am explaining. Here both the inputs are available in both normal and complement forms, right? So here you can observe A bar, B bar already available, you don't need to generate. So only external complement, that means we require 1. Similarly here, A bar, B bar already available, only for external complement we require 1, that's all. See the slight difference between the earlier case and here, right? Now coming to XOR gate, XNOR gate, when only normal inputs are available, that time you are getting for one case 4, other case 5, one case 4, other case 5. But if they mention the inputs are available in both normal and complement form, okay, whatever may be the case, whether with respect to NAND gate or NOR gate, the final answer will remain same. Okay, even in the gate exam, you don't need to do the simplification and then attempt. Just you can remember these are like direct answer you can remember. Okay, so the final answer will be 3. See, if you want here regarding these 4, I will give hint. Okay, whatever A XOR B expression is there. Okay, for one case I will explain. For other case you can try later. Okay, even that approach may help you while if they are giving other than logic gate, if they are giving any logic function, okay, that time how to proceed. So for that sake, I will give that approach. Okay, suppose if you are considering A XOR B, A XOR B is there. So A XOR B we can write it as A bar B plus AB bar. Now tell me this function is in which form? This function is SOP form. Here product term, these two are summed together. So whenever you are having the function SOP, we can easily implement by using NAND gates. Right? So see, with respect to Boolean function, we are telling it is SOP, and with respect to basic logic gates, you can correlate that one is like OR gate. You can observe A plus B format you are having. Similar format you can observe. This like you can consider like P, this you can consider like Q, P plus Q, OR gate format only. Here whatever the approach we have done, same approach you can proceed there, that's all, same approach. Here you have performed 2 times complement, and for inner complement you have used De Morgan's law. Same approach you can go ahead. So apply 2 times complement, and for inner complement you can use De Morgan's law. First term complement and second term complement, and keep external complement as it is. So here we are talking the condition that the inputs are available in both normal and complement forms, right? Normal and complement forms. So here you can observe A bar already available, B already available, A available, B bar available, right? So here we require 1, here second, here third. So we require 3 2-input NAND gates. Here we require 3 2-input NAND gates. Okay. Now the same XOR gate only, now we have to analyze what is the minimum number of 2-input NOR gates we required. Okay. So whatever the A XOR B is there, I am writing once again, A XOR B is equal to A bar B plus AB bar. But actually this function is in SOP form. Whenever SOP, it is easy to implement by using NAND. Okay. Now if you want to implement by using NOR gates, okay, we have to bring this function into POS form. Okay, regarding this we already covered in the previous session at the end. Okay, regarding SOP to POS conversion, that logic, with the help of that, now you can get. See, A bar plus A, you are getting what? 1. That combination you can avoid. Then A bar plus B bar, A bar plus B bar. The moment you have considered A bar plus B bar, the leftover variables you can consider. Leftover variables are A plus B. Whether your answer is correct or not, just you can verify. A bar into A, 0, plus A bar into B. Yes, we are getting this term. B bar into A, second term we are getting, then B bar into B is 0. Yes, we are able to, right? So this is the function. Now if you observe, it is in POS form. It is in POS form. Whenever you are having the function POS form, we can easily implement by using NOR gates, right? So now here, according to the logic function, you are having POS. Now you can consider this like P, this is like Q. P and Q, it is simply AND gate. You can observe AND gate. You are having AB. Whatever the approach here we have discussed with respect to NOR, we have performed 2 times complement, and for inner complement we have used De Morgan's law. Same procedure. 2 times complement. So here for inner complement you can apply De Morgan's law. You will get first term complement plus second term complement and keep external complement as it is. So here A bar plus B bar, then A plus B. Okay. So we are having 3 2-input NOR gates because A bar B bar already available, right? We require 3 2-input NOR gates. 3 2-input NOR gates. Okay, so in this way, if you want, you can give a try regarding XNOR gate, 2-input XNOR gate with respect to the last 2 columns. Okay, you can give a try, you will get the same answer, 3. Okay, here when both the inputs, that means when the inputs are available in both normal and complement forms, that time whether they are asking XOR gate or XNOR gate for 2-input case, the final answer will remain same. But if they don't specify anything about complement inputs in the question, so that means by default the inputs are available in normal form only, right? So when they mention like that, with respect to NAND gates we require 4 for XOR gate, with respect to NOR gates 4 we require for XNOR gate. Just remember for one case, if you are able to answer 4, obviously the other case is 5. Don't try to remember both. If you are remembering both, definitely in the exam you may get confusion whether it is 4 or 5. Okay. Just remember for one case, with the help of that you can answer for other. Just like here, if you are able to remember 4, other case you can answer for 5, that's all. So this is the another variety of question. Either they will ask with respect to minimum number of NAND gates or minimum number of NOR gates required for implementing any logic gate, and similarly any logic function. Okay, with respect to logic gates, you can remember AND gate approach or OR gate approach, how we have implemented, and similarly with the help of Boolean function means SOP form, POS form. So that is the reason we used to call NAND gates and NOR gates as universal gates, because we can implement by using NAND gates any logic gate. Okay, we see here in this tabular form we have implemented all other logic gates, yes or no? Similarly with the help of NOR. Okay, and here also with the help of these 2 examples we have given how we can easily implement any Boolean function by using NAND, because if you are able to represent SOP, we can easily implement. Similarly, regarding NOR gate, if you are able to represent in POS form, we can easily implement. Yeah, next chapter. So up to here we have discussed regarding first chapter, second chapter and third chapter. Now we are discussing regarding digital circuits. If you want to classify broadly the digital circuits, you can classify into two types. One is combinational, another one is sequential, right? So the next chapter is combination circuits. Chapter 4, combination circuits. So inside any combination circuit, you will be having logic gates. So that means logic gates are the basic building blocks of any combination circuit. Logic gates are the basic building blocks of any combination circuit. So here we are having various combination circuits. Okay, we'll discuss for every combination circuit, okay, what are the equations we are having, or whatever the important points are there, that we will cover. So the first one is binary adders. So regarding binary adder, we are having half adder. So the first one is half adder. It will perform addition of two inputs A and B. Both are having single bits. And it will produce two outputs. One is carry, another one is sum. So carry expression is A and B. Sum expression is A XOR B. Okay. Next one we are having full adder. Here full adder will perform addition of three single bits, or we can say three inputs. So regarding sum, you will get A XOR B XOR C in. Okay, regarding carry out, you will be having two expressions. One expression you will be having like A and B plus A XOR B and Cn. A XOR B and Cn. So this is one expression, and one more equivalent expression you will get for carry out. One more equivalent expression you will get for carry out, that is AB plus BC in plus Cn into A. So both are the equivalent functions for the carry output. According to the requirement, you can consider this equation or that equation you can consider. Okay. Suppose if you are considering this equation, just observe here, with respect to half adder, you are having XOR gate and then AND gate. Okay, like that you can observe here, XOR gate and AND gate. Okay, whatever A XOR B here you are having, same thing. Whatever A XOR B, same thing, right? So that means for implementing A XOR B and A and B, we require one half adder. After that you can observe, in order to perform XOR here, we can use one more sum expression here, and then here we have to perform AND operation. So for that we require carry. That means for implementing a full adder, we require two half adders, and in addition to that, either you may get carry here or you may get carry here in order to perform logical OR operation, right? So that's why we require one more extra OR gate. So for implementing a full adder, we require two half adders and one OR gate. For implementing a full adder, we require two half adders and one OR gate. The moment if Cn equal to 0, then full adder becomes half adder. So here with respect to adders, as we mentioned earlier, when you are performing addition, okay, we may require carry. Similarly, while you are performing subtraction, we may require borrow. So just like half adder, you will be having half subtractor. Just like full adder, you will be having full subtractor. Okay. So when you are considering with respect to full subtractor and half subtractor. So regarding half subtractor, just I am giving the hint regarding full subtractor. Okay. So whatever sum expression here you got, whatever sum expression you got here, okay. So the same thing you will get for difference. Same thing you will get for difference. That is A XOR B. A XOR B. Okay. And similarly here regarding difference, same expression. That is A XOR B XOR. Here carry in we have considered, there we will consider borrow input. A XOR B XOR Bn. So that means whatever XOR expressions you got here for sum, similar expression there you are going to get for difference. Okay. And coming to the borrow, here you got AB. Okay, wherever A is there, just consider A bar, that's all. Wherever A is there, just consider A bar. Okay. So coming to here borrow out, okay, you will get similar expression, but only modification is in place of A you can consider A bar, in place of carry in you can substitute borrow input, that's all. Okay, in place of A you can consider A bar, in place of carry in you can consider B in, you will get similar equation. Next, so with the help of full adders we can implement 4-bit binary adder. So in 4-bit binary adder, in 4-bit binary adder, in order to implement we can use 3 full adders and 1 half adder is sufficient, but for uniformity we will use all the adders or full adder only. For uniformity we will use all of them are full adders. Okay. So in this way, according to requirement, you can implement all the higher order adders just by cascading full adders. Okay. So regarding binary adder, here what are the binary adder we have told? Here this is 4-bit parallel binary adder, because we are given the inputs at the same time for every full adder, or the other name of this one is 4-bit ripple carry adder. 4-bit ripple carry adder. Because the carry output of one stage we are giving as carry input for next stage, that particular phenomenon is called ripple phenomena. Accordingly we are calling it as ripple carry adder. Okay. So regarding the 4-bit ripple carry adder or 8-bit ripple carry adder or 16-bit ripple carry adder, any number of bits ripple carry adder, they will ask the question regarding worst case delay, right? So worst case delay means we have to calculate the carry delay and sum delay at the nth stage full adder, or last stage full adder I mean to say. Okay. So worst case delay equal to maximum of TS and TC. Among the carry delay and sum delay at nth stage full adder, among those two whichever is the larger one, obvious that is the worst case delay. That means after you are given the inputs, in order to get the final output or in order to get the valid output, how much time we have to wait. That is nothing but worst case delay. Okay. In simple words you can write carry propagation takes place through all the stages. 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 Okay. So first of all, regarding carry delay, if you are having n stages, for every full adder, see, if you are considering what are the logic gates we have studied in the previous chapter, if you are considering all the gates are ideal, the moment you have given the inputs, you will get the output. That means there is no propagation delay. The moment you have given the input, you are getting the output. That means all the gates are ideal. When you are solving the questions regarding the third chapter, if they don't mention regarding any logic gate, there is a propagation delay. That means all those gates are ideal. But coming to this particular chapter or even in the previous chapter, if they mention for any logic gate, if there is a delay, okay, so that delay we have to consider. Okay. So here you can observe for carry you are having one AND gate, Okay, for some you are having XOR gate. Like that here, regarding full adder, if you consider, you are having 2 XOR gates, and regarding carry, you are having what? 1 XOR gate and 1 XOR gate, then 2 AND gates, and then 1 OR gate, right? So after you are giving A, B, C in A, B and C in are the inputs, in order to get the valid sum, it will take some time, and in order to get valid carry output, it will take some time. So after you are given the inputs, in order to get the valid sum, how much time it is taken, that is called sum delay, and in order to get the carry output valid, how much time it is taken, that is called carry delay, right? So for a full adder, they will give the information regarding sum delay how much, regarding carry delay how much. If they don't give, okay, then you can draw the circuit diagram with the help of this sum and carry out expression, and whatever the logic gates propagation they have mentioned, from there you can calculate from input to output. Just observe how much time maximum it is taking, okay, and from there you can calculate. After that, now what are the formulas I am going to discuss, based on that formulas you can calculate the worst case delay, okay, right. So here the carry delay at nth step full adder is equal to n times Tc, okay. Similarly, the sum delay at nth step full adder is equal to Ts plus n minus 1 times Tc. Ts plus n minus 1 times Tc. Here n is nothing but whatever the number of bits they are specifying, whether it is 4 bit, 8 bit, 16 bit, whatever the number of bit ripple carry adder they have mentioned, that number you can consider here. Among these two, whichever is the larger, that will be the answer. And for exam point of view, just to save the time, I am giving one more hint also. For a particular full adder, okay, they will give the information regarding sum delay and carry delay. So among the sum delay and carry delay, okay, suppose in general the sum delay will be more when compared to carry delay, okay. In most of the questions they will give like that, okay. If it is so, obviously at the last stage the sum delay only will be greater when compared to carry delay, right. Similarly, suppose if they have mentioned that sum delay and carry delay both are same, obviously at the last stage the sum delay and carry delay both will be same. Even if you calculate, you will get the same answer, okay. And suppose if Ts is less than Tc, that means carry delay is more, suppose, because ultimately it is a exam, right, theoretical, exam is a theoretical, right. Suppose if they want, they can frame the question like this: carry delay is more when compared to sum delay, obviously at the last stage the carry delay only will be greater when compared to sum delay, okay. So that's why no need to calculate both, okay, no need to calculate both. Now I have given the hint. Suppose if sum delay is greater when compared to carry, just calculate only sum delay at last stage, only sum delay. Now suppose if you consider any of these two cases, suppose sum delay is less when compared to carry delay, or sum delay and carry delay both are same, in this case better you can calculate carry, okay, better you can calculate carry delay. Why I am telling carry delay? The reason is very simple. Just observe these two equations. Which equation is very simple? Obviously carry delay, that's all, right. See, you can observe. Some of you might be wondering that, sir, how Ts and Tc will be same if Ts and Tc here same? You can observe here, in place of Ts you can substitute Tc. Here plus Tc, here minus Tc, both will get cancelled. N times Tc, N times Tc, both will give the same answer, right. That is the reason what I am giving conclusion point is very simple. If Ts is greater than Tc, then just calculate only the sum delay at nth step full adder, that's all, okay. Suppose if Ts is equal to Tc or Ts is less than Tc, that time just calculate the carry delay at nth step full adder, that's all, that will be the final answer, okay. So this is about regarding binary adders, binary subtractors, right. Then next one is magnitude comparator. Next one is magnitude comparator. As the name implies, it will compare the magnitude of two numbers, okay. Suppose I am considering A is n bit number, and similarly B is another n bit number, okay. After comparing these two numbers, we will give the relation whether A is greater than B or A equal to B or A less than B, okay. So that is one variety of question. They will give some circuit diagram, they will ask, okay. And another variety of question regarding this concept, they will ask that how many combinations A is greater than B, or how many combinations A is less than B, etc. Okay, so that time what you can do here, when you are making the truth table, you will consider regarding A n bits, regarding B n bits. Together how many bits you are having? 2n bits you are having together. Together you are having 2n bits. When you are having 2n bits, with the help of 2n bits, you will get total number of combinations are 2 power 2n. 2 power 2n combinations of zeros and ones you are going to get. These are the total number of combinations. 2 power 2n combinations of zeros and ones. Okay, here no need to remember all these formulas. Instead of giving 4-bit or 3-bit, I am making the generalized. Okay, right. So these are the whatever the n bit here, together you are having 2n bits. So with the help of 2n bits, you are getting 2 power 2n combinations. Now among these combinations, how many combinations we can say that both A and B are equal? Say for example, for easy understanding, you consider A is a 4-bit number and B is a 4-bit number. Okay, so here with the help of 4 bits, you will get 16 combinations. Whatever the combination you are considering for A, the same combination if you are considering for B, right? Suppose if you are considering A is like 4 zeros, okay, B also consider 4 zeros, or if you are considering 0001, 0001, 0010, 0010, 4 ones, 4 ones. Whatever the combination you are considering for A, the same combination if you are considering for B, then only we can say both A and B are equal, right? So that means with the help of n bits, you will get 2 power n combinations of zeros and ones. With the help of n bits, either you can consider with respect to B or with respect to A, you will get 2 power n combinations. Individually I am talking. So that many combinations will give A and B are equal. Now from the total combinations, if you are subtracting the number of combinations for which are giving for equal, okay, from there what you are going to get? You are going to get 2 power 2n minus 2 power n. So this many combinations of zeros and ones are going to give the relation as A not equal to B. See, the moment here you are saying A equal to B, from this many combination when you are subtracting from total, obviously what is the combination you are getting? That is A not equal to B. Now whatever the number here you got, just consider that number, divide with 2. Okay, whatever the number here you are going to get, that many combinations you will be having A greater than B, that many combinations you will be having A less than. That's all. Whatever the number here you are getting, that many combinations A greater than B, that many combinations A less than. Okay, whatever here we have discussed, if you want to verify, just consider n value 2 or n value 3, n value 4, your wish. Okay, and follow this approach, and then you can just give the conclusion whether whatever we have discussed, whether you are here for understanding purpose. Okay, I have given the generalized way. I haven't discussed 4-bit or 3-bit any case, but I have represented like this. Okay, but no need to by heart any equation. Just focus on the logic, or step by step whatever the procedure we have discussed, this procedure you can follow. With the help of this procedure, you can easily answer regarding the number of combinations, whether they are asking for A greater than B or A less than B, or even A equal to B also I have specified. Okay, so this is about magnitude comparator. The next topic is decoder. So decoder, as the name implies, it will perform the decoding operation, right? As the name implies, it will perform the decoding operation. That means at the input side you are having the coded information. That coded information, it is doing the reverse operation. That means encoding. Earlier with the help of encoder we can perform encoding operation, right? So with the help of decoder we will perform the reverse operation, right? So here generally the size of the encoder will be n to 2 power n. So you will be having n inputs, so it will be, you will be having 2 power n outputs. Okay, at any time only one among these 2 power n outputs will be equal to 1. Okay, based on the code available here, right? So at any time only one output equal to 1. So similarly, if you want, you can make volt also. Say for example, if you are making based on the code available here, at any time only one among the 2 power n outputs equal to 1, the remaining outputs will be 0. Similarly, you can make volta. That means only one among the 2 power n outputs you can make 0, the remaining outputs you can make 1. Like that also you can design, no problem. Okay. So for the timing, if you are considering that output, any one output equal to 1 at any time based on the code available here, right? So that time in general we will use enable also for the decoder. Whenever enable equal to 1, that time we are operating the circuit. When enable equal to 0, we are not operating the circuit. Okay. So if enable equal to 1, in general I am considering, if enable equal to 1, then the outputs of the decoder, then the outputs of the decoder are nothing but min terms. Okay. Similarly, if you are considering in another way, that means only one of the output equal to 0 and remaining outputs are equal to 1, that time we can call it as outputs are nothing but max terms, like that. Okay. Next one is encoder. Encoder, as the name implies, it will perform the encoding operation. So exactly the functionality of encoder is just exactly opposite to that of decoder. So in the decoder we have considered n inputs and 2 power n outputs. Now 2 power n inputs you will be having with the help of, when you are having 2 power n inputs, that many inputs we are coding into n inputs. Okay. So here the size of the encoder is 2 power n to n, and here regarding the normal encoder, at any time only one output equal to 1. Okay. At any time only, here input I mean to say. Okay. See here whatever the decoder outputs you are having, that decoder outputs now we are considering as inputs for encoder. So here earlier regarding the decoder we have told that at any time only one output will be equal to 1, right? So now those outputs only here as the inputs, right? So that means for a normal encoder, at any time only one input should be high. Okay. If you are getting more than one input high due to any reason, you may get the wrong code. To overcome that one, we will assign the priority to each input. Okay. If you are assigning priority to each input, then we will call it as priority encoder. So with the help of priority encoder, even if more than one input is high, you will get the code correctly. How you are able to get code correctly? Because when you are having suppose 4 inputs, among that if you have considered like the leftmost bit as a high priority, okay, at that time even though other 3 inputs also equal to 1, because you will get the code correspond to the leftmost bit, so since that bit also equal to 1, you will get the code correspond to it, like that. Okay. So with the help of priority encoder, whatever the drawback is there, with the help of normal encoder we can easily overcome. Yeah. Next one, demux. So here in general you will be having, for a demux you will be having one input line. Okay, you will be having one input line, and here you will be having 2 power n outputs, 1 by 2 power n. So the size of the demux will be 1 by 2 power n. So here whatever the one input you are having, okay, so that means you are taking the input bit by bit serially, right? So that serial input we are converting into, here 2 power n outputs you are having, right? Whatever the input you are receiving bit by bit, that particular input will be connected to one among these 2 power n outputs at any time. So based on the selection lines, here we will be having n selection lines. So based on this selection line code, we can connect that serial input to one among the 2 power n outputs. So that means we can call this demux as serial to parallel converter. So here application wise if you consider decoder functionality is what, at the input side you are having the coded form, we are doing the reverse operation, that means we are getting the decoding. Okay, coming to the demux, you are having serial input. Okay, with the help of selection lines we are connecting that serial input to one among these 2 power n outputs. Application wise decoder and demux both are different, but hardware circuit point of view there is a similarity. That means same hardware circuit you will be having inside the decoder and inside the demux. That is the reason we can use decoder as demux and demux as decoder. Okay, you can easily observe here number of outputs you are having 2 power n, that means that many AND gates you will be having. Okay, similarly in the n to 2 power n decoder also number of outputs are 2 power n, so that means that many AND gates you are having. Okay, that many AND gates you are having. And here whatever the selection lines you are having, whatever selection lines here you are giving, these selection lines in this particular circuit, if you consider, those are like coded information, right? So that's why we can use decoder as demux and similarly demux as decoder. We can use decoder as demux and similarly demux as decoder, since the hardware circuit is same. Since the hardware circuit is same for both. Application wise both are different, but hardware circuit point of view both are same, right? Next one, mux. Mux or multiplexer. Multiplexer in short we are calling it as mux. So just like decoder and encoder exactly opposite, similarly demux and mux exactly opposite. Here 1 by 2 power n, so just make the reverse. So here you will be having 2 power n inputs. So whatever the number of inputs you are having 2 power n at any time based on the selection lines. Okay, n selection lines you will be having based on the code available here. At any time one among these 2 power n inputs will be connected to the output. Since here only one output, we will call it as serial output, or you can say bit by bit you are receiving, right? So here number of inputs are there, that means multiple inputs, parallel lines we can say, and number of outputs are 1, serial, right? So based on that we can call it as parallel to serial converter. Parallel to serial converter. Parallel to serial converter. So for easy understanding, I am writing the standard equations for 2 by n mux and 4 by n mux. Output of 2 by n mux. So for 2 by n mux, here see 2 by 1 mux, that means n value is what? 1. So that means you are having one selection line. So output of 2 by n mux, y equal to, if selection line is 0, I0 will be connected. If selection line is 1, I1 will be connected. Right, S bar into I0 plus S into I1. Similarly, output of 4 by 1 mux. So in 4 by 1 mux, 4 you can write as 2 square. That means you are having 2 selection lines, S1, S0. So in this case, output expression you can write it as S1 bar, S0 bar into I0. That means when the selection values are 0, 0, okay, that time I0 will be connected. When the selection lines are 0, 1, S1 bar, S0, I1 will be connected. 0, 1 case, I1 will be connected. For 1, 0 case, I2 will be connected, and for 1, 1 case, I3 will be connected. Right? 0, 0 case, 0, 1, 1, 0, 1, 1. Okay, so regarding the multiplexer, Okay, in some questions they will give the mux and they will connect the selection lines, they will give the inputs, they will ask the output expression in the simplified function. Okay, or they can ask sometime in the standard function like sigma m form. Okay, whenever they are asking the simplified function, that time you can use directly this equation, and of course you don't need to write like that completely. In just by observing the inputs like I0, I1, I2, I3 in the given circuit diagram, whichever input values are 0, that combination you can ignore, because say for example I0 is 0, okay, that time this term is 0. When you are adding 0 to anything, resultant answer will not change, right? Answer will remain same. That is the reason whichever inputs are 0, that combination you can avoid. Whichever inputs are non-zero, that selection line combination you can consider, and the respective input combination you can consider. That's all. Okay. So regarding the muxes, you will get two variety of questions. One variety, they will ask the output function, or they will give the output function, they will ask the input. Okay. So you can do the option by option verification, or you can write the expression and then you can just correlate the output expression, and based on the given representation, and accordingly also you can identify among the choices which one is correct. Okay. And here one more interesting thing regarding mux. Earlier we have mentioned in the logic gates chapter, NAND gates and NOR gates were calling it as universal gates, because we can implement any logic gate by using NAND gates, any other logic gate by using NOR gates. Similarly, any logic function also. We have already covered that point. And similarly, regarding mux also, say for example, whatever the circuit or system you might be having, I am talking in terms of digital. Okay, if you want to represent the entire circuit, okay, with the help of single digital circuit, okay, you can easily implement with the help of single mux, provided the number of input variables for that circuit or for that logic gate, whatever the number of input variables you are having, choose that many as a selection line. That's all. Choose that many as selection line. So with the help of single mux, you can implement all the logic gates. In fact, any logic circuit or any digital circuit which you are having n inputs, you can replace that entire circuit or logic gate or logic function with the help of single mux. See, for easy understanding, suppose if you are considering like 2 input AND gate, suppose for a 2 input AND gate, you will get when you write the output expression. For easy understanding, I am writing. So output of 2 input AND gate, y equal to AB. Now you can observe AB you are getting where? Normal, right? So in here you are having total 4 terms. Among all 4 terms, only this term is having normal, right? So AB you are having, that means here S1 is A, S0 is B, like that you can connect for others also. Now I3 value we have to connect 1, I0, I1, I2 we have to make it 0, we have to make it 0. Okay, so here S1 equal to A, S0 equal to B, and then I0 equal to 0, I1 equal to 0, I2 equal to 0, and I3 equal to 1. See, just observe, when you are having 2 input AND gate, these are the values you will be having at the output side. Now at the input side you are having AB. Okay, now when you want to implement by using mux, AB you can choose a selection line. The moment you have chosen AB or selection lines, whatever the output column you are having, those output column you can map as the inputs for the mux. That's all. You no need to do any simplification at all. Whatever the logic gate or logic function you are having, you can implement that particular function, whatever the number of variable function it is, with the help of that many selection line you can consider. With the help of single mux, we can implement any Boolean function or any logic gate. That is the reason we can call mux as a universal element. Mux is a universal element. Mux is a universal element because we can implement any Boolean function or any logic gate with the help of 1 2 by 1 mux. Okay, sorry, with the help of a 2 power n by 1 mux, provided the number of input variables and number of selections both are same. Okay, so with this we have completed the 4th chapter, right? So the next chapter is sequential circuits, chapter 5. All of you put the heading. So in the combination circuits, output purely depend on the combination of present inputs, whereas in the sequence circuits, output depends on both present inputs and present state. Both present inputs and present state. Present state, or in other words you can call it as past output or previous output. Past output or previous output. Okay, current output depends on, okay, here output means present output, you can say. Present output depends on present inputs and the previous output. Okay, so regarding the, so that means whenever you want to give the previous output as one of the input for my next operation, obviously that previous output you have to store somewhere, that is called memory, right? So combination circuit along with memory, combinational circuit along with memory, combination circuit along with memory is known as sequential circuit. Combination circuit along with memory is known as sequential circuit. So regarding memories, okay, regarding the memories in this sequential circuits chapter, we are having examples are latches, then flip-flops, and then resistors. Latches, flip-flops and resistors are the examples of memory elements. Are the examples of memory elements. So here latches are level sensitive devices. Level sensitive means, say for example, I am considering enable signal. Okay, suppose this is enable signal. So here when enable equal to 1, okay, during this interval I want to store some bit. After that we will keep enable 0. Whatever stored value is there, that will be there permanently. Okay, similarly if you want, you can operate during enable equal 0. So any one level we are operating, so that means we are calling this is the level sensitive devices. Level sensitive devices. Whereas flip-flops, resistors, and later we'll discuss counters, all these are edge sensitive devices. Edge sensitive devices. So here flip-flops are edge sensitive devices. Edge sensitive devices. So here we will operate, okay, when the signal is changing from 0 to 1 or when the signal is changing from 1 to 0. So what are the enable signal we are calling, that same enable signal only, here we will call it as clock, because we have to give periodic waveform. Okay, because for every transition or for every signal, for every clock signal that changes from 0 to 1, we are going to operate that circuit, or for every clock signal that changes from 1 to 0, we are going to operate that circuit, right? So here 0 to 1 transition, that means it is a positive edge. It is a positive edge, or we can say it is a raising edge. Positive edge or raising edge. Similarly here 1 to 0, that means it is a falling edge, or we can say negative edge. Negative edge or falling edge. So regarding latches, we are having 4 latches. Similarly flip-flops, we are having 4 flip-flops. Regarding latches and flip-flops, the characteristic equations are same. Okay, so if you are able to remember those 4 characteristic equations, no matter the question, whatever the question you may be getting in this entire sequence circuits chapter, you can easily solve the question if you are able to remember those 4 characteristic equations. But only the difference, if they are asking with respect to latches, you will focus with respect to enable signal during 1. And similarly if you want As per the question, you can consider during enable 0. Okay, but generally if they don't specify anything, you can consider enable equal to 1. Okay, coming to the flip-flops or resistors or counters. Okay, so in general in the diagram they will represent like this. Okay, in the diagram they will represent like this. Suppose if you are having like this representation, that means here arrow symbol is there, right? Arrow symbol indicates edge sensitive, and here if you are having like this, that means here it is the positive edge. Okay, clock signal changes from 0 to 1. Suppose if you are having bubble, so that means clock signal changes from 1 to 0. Okay, just like normal gate and NOT gate, right? So whenever bubble is there, it is a negative edge. Okay, whenever bubble is not there, it is a positive edge. Okay, so from the given circuit you can identify whether it is positive edge or negative edge. In some question they will specify whether it is positive edge or negative edge. Okay, but the operation wise, what are the equations we are going to discuss now, those equations will be applicable when you are solving the question. But when you are, whatever the final conclusion points you will get, that will applicable with respect to positive edge and with respect to negative edge. But only the difference with respect to positive edge, if they have mentioned that particular operation is going to occur at that instance, whereas if they mention negative edge, at that particular instance you are getting like that. Okay, right. So write down the flip-flop name and then characteristic equation. So here first one we are having SR flip-flop. So the next characteristic equation is Q of t plus 1 is equal to S plus R bar Q. Q of t plus 1 equal to S plus R bar Q. Next one we are having D flip-flop. So D flip-flop equation is very simple. Q of t plus 1 equal to D. Q of t plus 1 equal to D. And then JK flip-flop, Q of t plus 1 equal to J Q bar plus K bar Q. J Q bar plus K bar Q. And the last one is T flip-flop, Q of t plus 1 equal to T exclusive R Q. T exclusive R Q. Okay, just remember these four characteristic equations. Among these four, D flip-flop and T flip-flop are dead easy, right? Q of t plus 1 equal to D, and here Q of t plus 1 equal to T XR Q, right? So here regarding D flip-flop, with the help of D flip-flop, we are able to store one bit, okay? Okay, if you want to store multiple bits, then we will connect multiple D flip-flops, then accordingly we are calling it as resistor. So with the help of resistor you can store n bits of information. With the help of D flip-flop we are storing 1 bit of information. So whenever, just for storing a bit, that time you can use D flip-flop, okay? But whenever if you want to use for other operations, okay, so you can use JK flip-flop or you can use T flip-flop. If you want to use SR flip-flop, you can use SR flip-flop, but only the first three conditions. Like regarding SR, 0 0 you can use, 0 1 you can use, 1 0 you can use. 1 1 case we should not use regarding SR, but 1 1 case we can use for JK flip-flop. Okay. So as I mentioned earlier, inside resistor you are having D flip-flops, right? So if that resistor is having the capability of shifting the bits, okay, so accordingly we are calling that particular resistor as shift resistor. So shift resistors, suppose if we are performing the shifting towards left hand side, accordingly we can call it as left shift resistor. Suppose towards right hand side if you are shifting, so accordingly we can call it as right shift resistor. So this is one classification based on in which direction the shifting is taking place. Okay. Similarly, we can classify the shift registers into other 4 types. Okay. How we are given the inputs into the shift register and how we are accessing the outputs from the shift register. Accordingly, we are having the 4 types: serial in, serial out shift register, serial in, parallel out shift register, then parallel in, serial out shift register, next parallel in, parallel out shift register. So in all these shift registers, if you want, you can consider right shift register or you can consider left shift register, no problem. Okay. So here you are giving input bit by bit, here you are taking output bit by bit, here you are taking the output, all the outputs at the same time. That means from every flip-flop you are getting the output at the same time, whereas here you are giving for every flip-flop input at the same time. Okay. So in this way we are having 4 types of shift register. Now if you observe overally, among these 4, obviously this parallel in, parallel shift register is the fastest shift register, whereas the first one is the slowest. Okay. Now by observing these 2, by observing the middle 2, here serial to parallel conversion and parallel to serial conversion we are doing. Serial to parallel and parallel to serial. Serial to parallel and parallel to serial. So earlier we have mentioned with respect to mux and demux, mux is doing parallel to serial, demux is performing serial to parallel. Okay. There we are performing with the help of selection lines, here we are performing with the help of clock signal. So this is about regarding shift registers, and from the shift register one of the application is shifting operation, right? And from here we are getting one more application that is called counter. Okay. So in general, for any shift register, if you are given the input from your side externally and if the shifting operation is taking place, then we will call that particular shift register as shift register only. That particular circuit we will call it as shift register. But somehow or other, if you instead of giving externally input from your side through some feedback mechanism with the help of some logic gates, if you are giving that input continuously to that circuit, then that particular shift register will produce finite number of states repeatedly, then accordingly we can call the shift register as counter. Okay. So here for one of the application we are getting based on the serial in, parallel shift register, we are going to have 2 counters. Okay. So the first one is, next one put the heading counters. So here we are having first one is ring counter. Suppose I am considering for n bit. In the ring counter we will consider this serial in, parallel shift register and the last output. Okay. The output of last stage flip-flop we are giving as serial input. So accordingly it is forming closed structure or ring structure. Accordingly we are calling the shift register as counter. Okay. So n bit ring counter. Okay. Here since it is n bit ring counter, okay, so it will be having n D flip-flops, okay, and it will produce n states, n unique states I mean to say. Okay. So the output frequency will be equal to input clock signal frequency divided by number of states n. Okay. Next one we are having n bit Johnson counter. Okay. The other name of this one is n bit twisted ring counter. See, in the ring counter we have considered the last stage normal output. See, for every flip-flop you will be having normal output and complement output. The normal output of last step we have connected as serial input. Then accordingly we are calling it as ring counter. Whereas in the Johnson counter, instead of normal output, we are taking the complement output of the last stage as serial input. Accordingly we are calling it as twisted ring counter. So here also the moment you are saying n bit, okay, sorry. Here I have considered n bit, okay, just one second. N I will consider small. the whatever the number of bits you are having, that many flip-flops you will be having. Okay, right. Now coming to the Johnson counter, when compared to the ring counter, you are getting the number of states are double. 2n states you are getting. So output frequency you will get f clock divided by, here number of states you are getting 2n, so that number will come into the denominator, 2n. Okay, with respect to shift registers, we are having two counters, one is ring counter, another one is Johnson counter. Okay, so these two counters are the examples of synchronous counter, because all the flip-flops will be having the same clock signal. Now we are having one more counter, okay, that is called ripple counter. The next one is ripple counter, n-bit ripple counter. So here the word ripple, okay, here this word ripple we already used in the earlier chapter also, that we have used for carry, ripple carry adder. Okay, similar word ripple we are using in this per day counter. So in this case, output of one stage we are giving as clock signal for next stage. Okay, that means in this circuit the clock signal is not same for all the flip-flops. That means we can say it is asynchronous circuit. But here what is the advantage of this ripple counter? Okay, that you will come to know in some time. Here with the help of n-bit ripple counter, here we are using n-t flip-flops. Okay, with the help of ring or Johnson, what is the number of bits you are having? Same number of d flip-flops. Whereas in the ripple counter we are using what is the number of bits you are having? That many t flip-flops. Okay. Now with the help of ripple counter, you will get all the states. Just like when you are having n bits, when I ask you to write all the combinations of zeros and ones, you will write all the 2 power n combinations, right? So in that way, with the help of ripple counter, we are able to get all the 2 power n combinations of zeros and ones. That means here you are going to get the number of states are 2 power n. So the output frequency will be equal to the clock signal frequency divided by 2 power n. See, with the help of ring counter or Johnson counter, we are unable to get all the states, because here we have used d flip-flops and internally the shifting operation will take place. Okay, so with the help of, say for easy understanding, if you are using 3-bit, okay, with the help of ring counter you are getting 3 states. With the help of Johnson counter you are getting 6 states. With the help of binary counter or ripple counter you are getting all the 8 states. 2 power 3 is nothing but 8. So this is with respect to these counters, but generalized case, they will use one term mod. Okay, that particular mod term they can introduce in front of any counter. Okay, so for easy understanding I am writing like this: mod n counter. Okay, for mod n counter, output frequency will be equal to input clock signal frequency divided by, here whatever capital N you are having, that is nothing but number of states. Okay, number of states. Yeah, with this we have completed regarding 5th chapter, that is sequential circuits, right? So whatever we have discussed up to here, that means starting from 1st chapter and up to 5th chapter, so it is for these 5 chapters are very, very important for all the branches, whether you are from EC or electrical or instrumentation, computer science. For all the 4 branches, the first 5 chapters are very, very important, especially for CS branch. Regarding the gate syllabus from the digital logic subject, only the first 5 chapters. Okay, so with this we have completed the syllabus for CS branch. Okay, now we'll discuss the remaining chapters. Okay, for other branches. So the next chapter is chapter 6, that is data converters. Chapter 6, data converters. So here we are having 2 types of converters. One is analog to digital and another one is digital to analog. Okay. So first I will discuss regarding digital to analog converter and then analog to digital. digital to analog converters. Later we will see analog to digital. Okay. So regarding digital to analog converters, we are having two types. One is binary weighted resistor type, binary weighted resistor type DAC. Binary weighted resistor type DAC, and another one is we are having R2R ladder, R2R ladder type DAC, R2R ladder type DAC. So whatever the equations, say for example, when they have given a digital to analog converter, in order to find the output voltage or in order to find the resolution or any calculation regarding digital to analog converter, whatever may be the circuit, okay, the calculation parameters wise both are same. Okay. So that we'll discuss in some time. Before that, say for example, regarding binary weighted resistor type I am talking, suppose if you are having 4 bits, just for easy understanding. Okay. So when you are having 4 bits, you will place the corresponding positional weights like this. Okay. In general, this is having minimum positional weight and this is having maximum positional weight. Accordingly, we used to call this is your LSB and this is your MSB. So this is the notation we have discussed in the first chapter, right? Now coming to the binary weighted resistor type DAC circuit diagram. Okay. So here you will be having number of bits, right? So for every bit correspondingly you will be having one resistor. Okay. So that resistor values you are having multiples of binary weights, That's why we are calling this particular DAC as binary weighted resistor type DAC. Okay. Now coming to here, whatever the positional weight here you are having 2 power 0, just multiply that one with R, 2 power 0 into R, that is nothing but 2 power 0 is nothing but 1 into R, that is R. Okay. Now similarly here 2 power 3 into R, 2 power 3 into R, that is nothing but 8 into R. Okay. So now how to remember? See, whatever this resistor you are getting, this particular resistor R we will give for here according to binary number, this is LSB, but this resistor we are going to give exactly opposite. That means this is your MSB. This is your MSB resistor. For MSB bit we are giving this resistor value, and whatever you are getting here 8R, this resistor value we are going to give for LSB. So in simple words, what you can do, just unsigned case, you know how to write the binary weights, just write as it is, and you know what is LSB, what is MSB. Now consider LSB weight multiply with R, just swap. In place of LSB, whatever the resistor value you are getting, that you give for MSB bit, resistor I mean to say. Okay. Similarly, whatever the position weight you are getting for MSB, multiply with R. Since you are having MSB, this particular resistor we are going to give for LSB. Okay. So in some question they will ask that, they will give MSB resistor, they will ask LSB resistor, corresponding LSB resistor, or they will give LSB resistor, they will ask MSB resistor. Okay. But in some questions they can easily ask, they will give the minimum value of the resistor and they will ask the maximum. Whenever the minimum and maximum, that time you don't need to worry too much about which is the MSB, which is the LSB resistor. But sometime when they are asking specifically regarding the MSB resistor or regarding the LSB resistor, that time you have to careful. So with this easy understanding, you can easily answer those kind of questions. No need to have any confusion, no need to remember or by heart the circuit, not at all required, Okay. So coming to either first type or second type, DAC. Okay. So that means you are having input what? Digital or binary, and output you are going to get analog form. So output of DAC, whenever they are asking to calculate output of digital to analog converter, so whatever the digital input that you are giving, digital input or binary input, both are same. Okay, as for exam point of view, you can consider both are same, but for interview point of view, there is a slight difference. The word binary means you are representing the values in terms of zeros and ones. The same values when you are representing in terms of electrical signal, like 0 means 0 volt, 1 means 5 volt. That means you are getting electrical signal in terms of 2 voltages. That one we are calling it as digital signal, right? So output of DAC is equal to decimal equivalent of decimal equivalent of digital input or binary input into resolution. Decimal equivalent of digital input or binary input. Okay, this knowledge you already got from the first chapter, you can do it. And regarding resolution, in some question they will give, and in some question if they not give. Okay, regarding resolution you are having one more formula. Resolution equal to full scale voltage or reference voltage all are same, or maximum input voltage all are same. Okay, V full scale divided by 2 power n. V full scale divided by 2 power n. Okay, by using this formula they will mention whether 4-bit DAC or 8-bit DAC. So from there you will get n value, and full scale value they will give 5 volt or 8 volt or 10 volt, that you can substitute. Okay, so from here you can calculate. In some question they won't give the maximum input voltage or reference voltage, full scale voltage, they won't give. Okay, but they will give the clue. Okay, so in another way they will give. So regarding that I am writing, okay, resolution is nothing but the output of DAC, when only LSB equal to 1, and remaining all other bits are equal to 0. Okay, so when you are having suppose n bits, okay, among those n bits you are considering only LSB 1 and remaining all the bits you are keeping 0, that time whatever the output you are getting, that is nothing but resolution. Okay, in simple words, say for example when you have considered all the inputs are 0, by default you will get output as 0. That means in order to observe the minimum change at the output, okay, that minimum change, in order to observe at the output what minimum change you can make at the input, that is only possibility when you are keeping LSB as 1. Okay, so that is the reason in some question they will give, okay, suppose if it is a 4-bit number, okay, they will mention like for 0001, that time they will give the output. That is by default in the question nowhere they specify that is the resolution, but you can catch that one. Okay, because when you are having all the inputs are 0, definitely you will get output as 0, but when you are giving 0001 for 4-bit case, you will get something as a voltage as the output. When they mention, obviously that is a resolution, right? So that resolution you can use. Okay, in some question based on this logic you can use, and in some question whenever they are giving full scale voltage and number of bits, from here you can calculate. Okay, so this is regarding digital to analog converters. Now coming to the analog to digital converters. Analog to digital converters. So here we are having 3 types of converters. One is counter type ADC. So in short I am writing. Second one is successive approximation type ADC. And the third one is flash type ADC. Flash type ADC, right? So in the counter type ADC, the maximum conversion time is equal to 2 power n minus 1 times clock signal time period. Okay, whereas in successive approximation type ADC, the maximum conversion time is n times clock signal time period. Whereas in the flash type ADC, the moment you are given the input, if you are considering whatever the priority encoder you have considered or whatever the comparators you have considered, if you are assuming all are ideal, the moment you are given the inputs, you are getting the output. In no time you are getting the output. So among all the ADCs, this is the fastest ADC. Among all the ADCs, it is the fastest ADC. Okay, and here the other name of this one is parallel type ADC. because here the comparison operation is performing in parallel, okay. And here regarding parallel type ADC, we require, in parallel type ADC we require 2 power n minus 1 comparators. We require 2 power n minus 1 comparators. Okay. With the help of all these ADCs, we are getting the output in digital, output in the digital form, but with the help of counter type ADC, when you observe all of these, obviously it is taking more time. The moment you have given input, in order to get the valid output, it is taking more time. Whereas successive approximation, we can say like moderate. Suppose if you are having 8 bits, it requires 8 clock cycles, maximum conversion time I'm speaking. And whereas the flash type ADC, the moment you are giving the input, you are getting the output. Okay. So in general, according to the requirement, you can use the corresponding ADC. Wherever the speed is not a, wherever the time is not a constraint, that time you can go for counter type ADC. But suppose if delay is a constraint, that time you can go for either flash type ADC or, okay, among all, the best is flash type ADC. But if you want to go for moderate applications, you can go for successive approximation ADC, right? So with this, we have covered regarding data converters. So we have discussed regarding digital to analog converters and regarding analog to digital converters. So regarding these converters, whatever the concepts operation is there, just you can go through, you can refer your notes in your free time. Okay. So here in this particular session, I have just discussed whatever the important points and formulas are there regarding digital to analog converters and analog to digital converters, right? So with this, we have completed the syllabus for electrical branch, right? So for electrical branch, regarding digital circuit subject, the syllabus is up to 6 chapter. Okay. Now we will discuss one more chapter, that is the last chapter, that is common for EC and instrumentation. Okay. So the last chapter, that is CMOS logic family. CMOS logic family. So here in this particular logic family, we are using 2 types of transistors. One is NMOS transistor, another one is PMOS transistor, or the other name of this one is N channel MOS and here P channel MOS. Okay. The functionality of these two are exactly complement to each other. That is the reason we are calling it as complementary MOS. CMOS full form is complementary metal oxide semiconductor. Okay. So NMOS will be on if VGS is positive and VGS is greater than VT. VGS is greater than VT. VT means some threshold voltage or cut-in voltage. Just like diode, you will be having, ideal diode means 0 volt cut-in voltage, but for all the practical diodes, you will be having 0.2 volt or 0.6 or 0.7, etc. So like that. Okay. Similarly for PMOS, PMOS will be on if gate to source voltage is negative, and when you are considering modulus, VGS value should be greater than modulus of cut-in voltage. Okay. When you are solving the questions regarding NMOS and PMOS in the analog circuit subject, so they will specify regarding the threshold voltage or cut-in voltage that you can consider, like 0.2 volt or 0.3, etc. But coming to this particular digital circuit subject, okay, regarding threshold value, you can assume like 0 volt. Okay. Like ideal case you can consider. The moment you have considered ideal, so here you can consider VGS is positive and VGS greater than 0. So in simple words, you can say that VGS value should be greater than 0. For NMOS, VGS value should be greater than 0. Whereas for PMOS, VGS is negative and modulus when you consider, that should be greater than 0. Yes. So in simple words, you can say, so with respect to PMOS, when you are analyzing the questions with respect to our digital circuit subject, you can consider like VGS less than 0. The moment you are getting VGS less than 0, PMOS will be on. If you are getting VGS greater than 0, then NMOS will be on. Suppose if you are getting VGS is 0, then both NMOS and PMOS both are off. Okay. And here one more interesting thing regarding CMOS logic. Okay, in general, in the circuit, okay, you will be having, here we are using transistors of MOS type, metal oxide semiconductor. So that is the reason we will use the supply as VDD. okay, and ground as reference, right? In between we will take the output, okay. Between output and VDD, between VDD and output we will use PMOS logic or PMOS transistors. Between output and ground we will use NMOS transistors. And from where you are taking the output, by default you will get the output expression in the complement version in the CMOS logic, okay. The reason is very simple. Here you can observe NMOS we are connecting between output and ground. NMOS, in order to make on, we have to give high voltage at the gate terminal. When you are giving high voltage at the gate terminal, then the corresponding NMOS is on. If it is on means the corresponding drain and source terminals are shorted, so output is connecting to ground. So you are giving high as the input, but you are getting low as the output. Similarly, vice versa. That is the reason in the CMOS logic family, by default you are getting the complement version in the output expression, right? So regarding CMOS logic, you will get two variety of questions. One variety is they will give the circuit diagram based on CMOS logic. They will ask the output expression. That is one variety of question. Another variety is they will specify any logic gate or they will give any logic function, and they will ask for implementing that particular logic function or logic gate how many NMOS PMOS transistor pairs required. See here, when I say pair, okay, see here NMOS, suppose if you are using 10 NMOS transistor, okay, same number we will use for PMOS, okay, 10 PMOS, 10 NMOS. Individually talking together, we are individually talking, total number of transistors are 20, but pair-wise 10 only. Whatever the NMOS transistors you are using, same number you are using for PMOS. So in general, NMOS PMOS transistor pair, we will call it as pair, transistor pair, okay. So just if you are able to count NMOS transistor, the same number will be for PMOS, the same number will be for NMOS PMOS transistor pair, okay, right. So now I will give the tabular form, okay, regarding for every logic gate, what are the logic gates we have studied in the third chapter. For all those logic gates, how many NMOS PMOS transistor pairs required, just by observing the expression, how easily we can write, that one I will discuss, and for whichever other cases you can remember at this point of time, I will discuss, because this is not the regular class, that's why I won't discuss more in detail, but wherever required, it is easy to explain in less time, I will definitely cover, but wherever, just like in the earlier also, XOR gate, XNOR gate, it is taking more time, because this is not the regular class, it is a revision class, that's why I have directly given the answer, right. So all of you make the tabular form. So here you can write down logic gate, and here you can write minimum number of NMOS PMOS transistor pairs. Minimum number of NMOS PMOS transistor pairs required. Minimum number of NMOS PMOS transistor pairs required. Right. So first one is NOT gate. NOT gate. Output is what? Y equal to A bar. Y equal to A bar. Just observe, you are having complement version. Yes. By default, you will get complement version in CMOS logic. Under the complement, you are having only one variable. That means we require one NMOS and we require one PMOS, together one NMOS PMOS transistor pair. Next one NAND gate. NAND gate. For easy understanding, I am considering two input NAND gate. Y equal to AB bar. Just like this expression, you are having complement. Yes, complement, no problem. But under the complement, you are having two variables. That means we require two NMOS. and similarly 2 PMOS. Okay, together 2 NMOS PMOS transistor pair. Okay, after that, just one second. Here I will write regarding NOR gate. Regarding NOR gate, here y equal to a plus b whole bar, a plus b whole bar. So here also under the complement you are having two variables. That means 2 NMOS, 2 PMOS. Okay. Regarding connection wise, okay, if you want more clearly, here A and B, and means what? Series connection. So that means NMOS transistors will connect in series, the corresponding PMOS in parallel. Similarly here A plus B. A plus B means logical OR operation. So NMOS will connect in parallel, the corresponding PMOS in series. Okay. So here also we require 2. Now corresponding complement, that is AND gate. AND gate. So here AND gate output is A and B. But here just now we have mentioned by default with the help of CMOS logic you are getting complement version, right? So now you can perform 2 times complement. Now regarding this one we already discussed, we require 2, and now for this one we require 1 more. So 2 plus 1, that is 3. 2 plus 1, that is 3. Similarly here OR gate. Similarly here OR gate. OR gate y equal to a plus b, but here you can perform 2 times complement. Regarding this one we have already seen just now 2, and then here complement, so 1. 2 plus 1, that is 3. 2 plus 1, that is 3. Okay. Now the remaining gates, those are XOR gate and XNOR gate. Y equal to a XOR b, y equal to a XOR b, and another one is XNOR gate. Okay. So regarding XOR gate, XNOR gate, you will get here 6. Okay. So here just for easy understanding, for one case I will discuss, for other case if you want you can try later. Okay. Because this approach may help you, okay, while solving the question. So that is the reason I am giving. Say for example A XOR B you are having. A XOR B you want to implement. Now what we have mentioned so far, whenever you want to implement by using CMOS logic, by default you are getting output in the complement version. But here A XOR B you are having, right? But you don't have any overall complement. Now what we can do, okay, so sometimes students will be too smart that, okay, what they will tell is just like we have performed for AND gate 2 times complement, OR gate 2 times complement, the same way they will apply. Of course you can implement, no doubt about it, but if you are going like that, if you are doing like that, you won't get minimum number of NMOS PMOS transistor pairs required. You may get, okay, you may get some value, but that value is not minimum. Okay, if you want you can give a try later. Okay, now you have to try to understand the logic that we have mentioned. Say for example before implementing AND gate I have implemented what? NAND gate first. Similarly before implementing OR gate first I have implemented NOR gate, because here the expression itself by default you are having complement, right? So now I am applying that logic. Now can you guess at least? I already given the hint. Now I want to implement XOR. Now I will take the help of XNOR gate. Yes or no? So complement of XNOR is nothing but XOR. Complement of XNOR is nothing but XOR. Okay, right. So now you can write the expression. A XNOR B is nothing but AB plus A bar B bar. AB plus A bar B bar. And then overall complement you are having. Yes, when you are having overall complement, directly you can implement by using CMOS logic. That is the best advantage, right? Now in this expression, okay, overall expression if you observe, you are having complement. See, overall expression if you are having complement, no need to worry. By default you are getting the output in the complement version. No need to worry, right? Now just focus under the complement what are the terms you are having. Okay, for the timing if you don't have this term, okay, you are having AB. So that time, okay, sometimes few students will be too smart, they will consider AND gate. No, don't consider that one. Here for the timing if you ignore the other term, you are having what? AB bar, right? So just focus here, AB bar. Regarding that you are having what? 2. So here 2 variables are there, you require 2 NMOS, the same number for PMOS. Similarly here you are having A bar B bar. See, in general in the question they will if they are not specifying anything about inputs, that means by default they are available in normal form. Okay, so wherever you are getting complement, we have to generate. Okay, so first of all, for easy understanding, for A bar we require one NMOS, right? Similarly for B bar we require one NMOS. Now you assume that A bar is like X and B bar is like Y. Now XY you are having. So for XY, just like AB, XY we require 2. Okay, so we require 2. So I hope all of you are getting the clarity. See, if both the variables are normal, okay, since you are having 2 variables, that many NMOS. Okay, here both the variables are complement, so that is the reason. Okay, that is the reason we are getting 2 extra. I hope all of you are getting clarity. Okay, suppose if you are having only A, okay, suppose if you are having A into B bar, okay, B bar you can consider like Y. A into B bar, 2 variables are there, 2, and for B bar you can consider 1 because it is in the complement. Okay, so now whatever you got, now you can add. Okay, so here 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 2 is 6. So from here we are getting 6. Okay, 6 NMOS PMOS transistor pairs. Similar logic, XNOR gate you can write as complement of XOR. From there also you will get 6. Okay, so with this we have completed the syllabus for all the branches. Okay, up to here whatever we have discussed, this is part of the gate syllabus for digital circuit subject for EC branch and instrumentation branch. Okay, so regarding the digital circuit subject, so among the 7 chapters, the first 5 chapters are very, very important for all the 4 branches. As I mentioned earlier, whether you are from EC or electrical or instrumentation or computer science, the first 5 chapters are very, very important. Okay, so as for CS branch, the syllabus is up to first 5 chapters, whereas for electrical branch, the syllabus is up to 6 chapter, whereas for EC and IN, all the 7 chapters. Okay, so in the previous session and this session together, in these 2 sessions, we have completely revised the entire digital circuit subject. Whatever the important points, formulas are there, which are going to help you in your coming GATE exam. So I have discussed each and everything. So all of you, I hope all of you got the command over the digital circuit subject. In less time, you people have got the glimpse of digital circuit subject. So in your free time, if you want, you can refer your classroom notes, whatever with you. Okay, if you want more, okay, you can just refer the notes. But in this limited time, in the around 3 hours time, we have discussed entire digital circuit subject. I hope all of you got great impact. Okay, in 3 hours time, you are able to get complete overview of entire digital circuit subject. So all of you just focus on whatever the leftover days are with you. Okay, don't try to study any new thing. Okay, whatever already you have studied, just try to remember or recall whatever you already learned. Okay, and if you want, for every subject chapter level, whatever the important concepts are there, just try to recall the concepts, and whatever the methods of solving are there, just try to recall, so that when you are recalling, you are getting the command over the concept. Okay, definitely that will help you in the coming GATE exam. The moment if you start studying new things, okay, then what will happen? You are in the studying mode. Okay, so always your mind or your eyes will feel that you are studying something new. But of course, coming to the smart revision sessions, whatever happening in our IMS GATE Academy channel, so all of you can attend, so that what will happen, because in these sessions you are not learning something new. In fact, we can say that whatever you already studied, we are just helping you just in order to get the complete revision in the less time, right? So, and in fact, you are getting the association of our faculties, so it's a great advantage, because as the exam date is coming closer, generally the students who are studying independently at their home, definitely sometime they will be having very high level, confidence level, but sometime they may get the confidence level may go down. Okay, so if you people, if you are able to attend our series, based on your available time, try to attend the session live, and due to any reason if you couldn't attend the session in live, at least you can watch the recorded lecture, so that you will get the same equal experience, you will get the same benefit you will get. Okay, no issue at all, because the lecture is available in the recorded form, so you people can watch at any point of time and try to get the maximum benefit from this series of lectures. So in today's session regarding digital circuit subject, the smart revision we have done in 2 sessions. Similarly, on tomorrow I am going to come on live. Okay, similar timings, 1:30. Okay, 1:30 to 3 and then 3:30 to 5. Okay, so I will be coming on live for one more subject, that is the communication subject, which is common for EC and instrumentation, right? So I hope all of you will come tomorrow on live. So we'll meet you all on tomorrow. In those 2 sessions, communications is one of the a core subject of EC branch, and in fact the syllabus wise very vast. But no matter whatever the syllabus, okay, I am going to cover around within 3 hours or around 3 hours I am going to cover. So all of you will get the complete whatever the important points are there, formulas are there, especially in communication system subject, lot of equations will be there, right? But all of you will get familiarity. Tomorrow I am going to come on live in 2 sessions. Together I will be complete revision I am going to do. Okay, so don't miss tomorrow's 2 sessions. So whoever targeting for 2024 GATE exam. Okay, so thank you everyone. We'll meet you all on tomorrow.